Hello students, welcome to All Force e-learning channel. This is K. Nageshwar, your physics faculty. Today we are about to deal with session number 105, second year Neet. And the chapter name is Magnetism and Matter. This chapter was started in the previous session. So let us briefly recollect what has been completed in the previous session. Magnetic length. We have come to know that magnetic length and geometric length of a bound magnet are not same. Okay, both are different. And the relation between magnetic length in the sense the shortest distance of separation between north and the south poles of a magnet, that is called as magnetic length. So the relation between magnetic length and geometric length in the sense end to end length of a bar magnet. Okay, so this is the relation. Magnetic length is equal to 5 by 6 of geometric length. And this is another equation that we have talked about yesterday. It's a magnetic dipole moment equation. Magnetic dipole moment is equal to pole strength multiplied with magnetic length. 2L is magnetic length. So this is the bar magnet that we have considered. So this capital L is a length, geometric length, and this 2L is magnetic length, separation between south and north poles. Okay, so we have also discussed about cutting a magnet and how magnetic dipole moment changes. So if a magnet is cut like this, perpendicular to length of the magnet, then the magnetic dipole moment of each piece, okay, will be m by n if it is cut into n pieces. If it is cut into n pieces. If it is cut n times, how many pieces will get? Will get n plus 1 pieces. And if that is the case, each piece magnetic dipole moment will be m by n plus 1, where m is the total magnet's magnetic dipole moment. Okay, this m dash is, magnetic dipole moment of each piece. After cutting whatever pieces you will be getting, each piece magnetic dipole moment is m1. Okay, if the magnet is cut parallel to its length, then again, magnetic dipole moment of each piece is equal to m by n. Okay, so it is cut into n equal parts. If it is cut n times, we will have n plus 1 pieces. Okay, these are the points that we have discussed. And we have also talked about cutting a bar magnet parallel to its length and perpendicular to its length. X equal parts parallel to its length, y equal parts perpendicular to its length. If that is the case, magnetic dipole moment of individual piece, we have derived that equation to be as m by xy. Okay, so now let us try to solve this question. What is this? The length of a magnet is 16 centimeters. 16 centimeters. Magnetic length 2L is given as 16 centimeters. Its pole strength is 250 milliamp meter. When it is cut into 4 equal pieces parallel to its axis, the magnetic length, pole strength, and the moments of each piece are. So he is asking about each piece length, pole strength, and magnetic moment. And it was cut into 4 equal pieces parallel to its axis. This is how it was cut. 1, 2, 3, 4 pieces. So individually these pieces length, it remains constant. The parent magnet's length, whatever length it is having, 16 centimeters. Individual piece length also 16 centimeters only. So there is no any change in the length. Whereas pole strength, it is going to change. Pole strength is something that is connected with the cross-sectional area, isn't it? So it will change. And if pole strength changes, of course, moment also changes. Magnetic moment also changes. So here pole strength is given as a 250 milliamp meter, isn't it? The units of pole strength are ampere meter, isn't it? So it is given as 250 milliamps meter. And the length of the magnet is given as 2L is equal to 16 centimeters. Number of pieces, into how many pieces this magnet was cut? Into 4 pieces it was cut. So magnetic length 2L, it's given as a 16 centimeters. And here pole strength of each piece, it becomes 1/4. Earlier it is m, now it is divided into 4 equal pieces. So here cross-sectional area becomes 1/4 of initial cross-section. So pole strength also becomes 1/4. So 250 by 4. 250 is what? The pole strength of the given magnet. Whatever actual magnet is taken, that magnet's pole strength is 250 milliamp meter. So 250 by 4 gives us a 62.5 milliamp meter. So here magnetic length of each piece is equal to 16 centimeters and pole strength of each piece is equal to 62.5 milliamps. If magnetic length and pole strength both are known to us, can't we find the magnetic moment? Of course, we can find. So magnetic moment can be expressed as magnetic moment of each piece m dash is equal to each piece magnet what a pole strength into length of the magnet. So m by 4 into 2l. So each piece pole strength is how much? M by 4, and each piece length is how much? 2l. So here m by 4 has been already calculated. It's a 62.5 milliamp meter. I have replaced it here, and 2l is what? 16 centimeters. Here, whatever meter is present, that meter is converted into centimeters, so that we have written 100 here. 1 meter is equal to how many centimeters? 100 centimeters. Okay, because 2l is in centimeters, so this is also converted into ampere centimeter. Right. So finally, if we multiply this, what did we get? 100 amp centimeter square. Okay. So if it is further reduced into meter square, it becomes 0.01 ampere meter square. So this is the answer. Okay. Now let us talk about this. Variation of magnetic moment due to bending of magnets. So I'm taking a magnet like this. Now it is bent like this. So when the magnet is bent like this, what changes are you going to see? Let us try to understand this picture. Here, the separation between South Pole and North Pole is, like this, linear. Here, the shortest distance of separation between South Pole and North Pole is this one, isn't it? So the separation between South Pole and North Pole has changed when the magnet is bent. Whereas the cross-section area remains constant, right? So here, whatever cross-section area is present, the same cross-section area is also present here. So it means pole strength remains constant, but length of the magnet is what? Shortest distance between south and north pole. Here, if it was bent like this, what is the shortest distance between south pole and north pole? This one, isn't it? You cannot take length along this curved line, isn't it? So shortest distance will be this one. So now what has happened to the separation between south pole and north pole? It is reduced. If it is reduced, what will happen to the magnetic dipole moment? It also decreases. Pole strength is constant. Okay, magnetic length has decreased, so m into 2l will be small when compared to this case. Here magnetic dipole moment will be more when compared to this magnet. Okay, so what are the observations that we have made here? When a bar magnet is bent, magnetic length decreases. Yes, if it is bent, magnetic length decreases. Its pole strength remains constant. Pole strength remains constant. Therefore, magnetic moment decreases. Yes, magnetic moment will decrease. Now see, when a thin bar magnet of magnetic moment m is bent in the form of U shape with the arms of equal lengths as shown in figure. So he is talking about a situation. See here. One bar magnet is taken, a thin bar magnet, and it is bent in the shape of a U, such that this arm length and this arm length and this arm length all are having same length. Okay, so this is south pole. If this is south, this will be north. If this is north, this will be south. You cannot imagine two like poles just side by side adjacent. That's not possible. Okay, they don't exist just side by side. So if this is north, this is south. If this is south, again this is north. If this is north, this is south. And if this is south, this is north. Since this thin magnet is bent in the shape of U with the lengths, side length with arm's length equal, then the individual magnetic dipole moments, if total magnetic dipole moment of this bar magnet is m, this part's magnetic dipole moment will be m by 3, this part's magnetic dipole moment will be m by 3, this part's magnetic dipole moment will be m by 3, because all are of same length. I will consider one coordinate system here. Let us say this is x-axis, this is y-axis. Now if you compare this picture with this one, magnetic dipole moment m by 3, here it is in the downward direction, or by taking this as a reference, you can say that this particular magnetic dipole moment m by 3 is along negative y direction. Yes, magnetic dipole moment is a vector quantity, so you can make use of this coordinate system to represent the direction. Okay, and what about this m by 3? This m by 3 is along positive x direction. This m by 3 is along positive y direction. So since the directions are known to us, let us write the resultant magnetic dipole moment of this U shape. Okay, it can be written like this: m1 bar is equal to magnetic dipole moment of this one is along negative y direction. So how much is the magnetic dipole moment? M by 3, and it is along negative directions, negative y direction. So that minus j cap is taken here. So m by 3 into minus j bar plus this one is along positive x direction. So m by 3 I cap, and this one along a positive y direction. This is along positive x direction. So m by 3 I cap, and this is along positive y direction. M by 3, what you will have? J cap. Okay, so if you observe this one carefully, here you are having m by 3 minus j, here plus m by 3 j. So these two things gets cancelled, and finally you are left with only m by 3 I. So m by 3 I is what? The resultant magnetic dipole moment of this U-shaped arrangement. Okay, so magnitude is written like this. Let us talk about another case. When a thin bar magnet of magnetic moment M is bent at the middle so that the two equal parts are perpendicular as shown in the figure, like this. So a thin magnet is bent such that the two equal parts are perpendicular to each other. It is bent exactly at the middle. Okay. And now if you are supposed to measure the magnetic length, this is how magnetic length can be calculated. Okay, 2L dash is magnetic length. Since this part length and this part length both are same, so magnetic dipole moment of this side can be written as m by 2, and this particular magnetic dipole moment can also be written as m by 2. Let us take a coordinate system as a reference, because here two different directions are there. In the upward direction, like that is along a positive y direction, m by 2 magnetic dipole moment is existing, and along negative x direction, this one, okay, this m by 2, it is along negative x direction. Okay, so let us write an equation for the resultant magnetic dipole moment. M1 bar is equal to m by 2 minus I cap. This is along negative x direction, so that minus I bar is taken here, plus m by 2 j cap. This is along positive y direction. The resultant will be under root m by 2 whole square plus m by 2 whole square, isn't it? If it is further reduced, you will have under root 2m square by 4, and if it is further simplified, you will have root 2 into m by 2, which is equal to, after rationalization, you will get m by root 2. So the resultant magnetic dipole moment is m by root 2. And this can be approached in different ways also. If you can manage to find out to 2L dash, pole strength is constant only, m, small m. Okay, so m into 2L dash can also lead to the same conclusion. M dash is equal to m by root 2. Okay, so let us talk about one more situation. When a thin bar magnet of magnetic moment M is bent into an arc of circle subtending an angle theta radians at the center of the circle. This is a kind of general case. So a thin magnet is taken and it is bent like this. Okay, such that the arc is making an angle theta at the center. Okay, and the separation between these two poles, as you see here, y plus y, 2y is the separation. So what is the magnetic length here? 2y. If you try to find out magnetic dipole moment here, pole strength will be multiplied with 2y. But we don't know what this 2y is, isn't it? So radius of curvature of this bent magnet is capital R. So what is this arc length? Arc length is what? 2L. Because initially this is a magnet of length 2L, and now it is bent such that it makes an angle theta at the point O here, like it is shown in the figure. So here m dash is equal to what? Pole strength. Pole strength, either S pole strength or north pole strength, anything can be taken. M into separation between these two poles, 2y. But we don't know what this 2y is. Let us try for this 2y. Okay, so here in this right angle triangle, sine theta by 2 can be written as opposite side by hypotenuse, pi by r. Therefore y is equal to r sine theta by 2, isn't it? And what do we need? We need 2y. Just multiply this with 2. Okay, you will get 2y. And before that, we don't know what this r also. We don't know this r. When this kind of details are given in the question, will be given with only 2L and pole strength value. That's it. This capital R and all we don't know. Even theta value will be given to us. Okay. So let us replace this r also with the known terms. Theta can be written as arc length by what? Radius. So r is equal to 2L by theta. So this 2L is known to us. This theta is also known to us. Now I can replace this capital R with 2L by theta. Okay. So effective length is equal to 2y, which is equal to 2 into y is what? R sine theta by 2. So 2r sine theta by 2. And if r is replaced with 2l by theta, because r is 2l by theta, you will have 2 into 2l by theta into sine theta by 2. So therefore m dash, okay, replace this 2y here. What you will get? Small m into 2y. 2y is this one, right? Okay. Now, what is m into 2l? M into 2l is nothing but magnetic dipole moment of the magnet before it was bent, isn't it? So I can replace that m into 2l with capital M. So m into 2l is replaced with capital M. So finally, what is the conclusion? 2 into m sine theta by 2 by theta. So this is the magnetic dipole moment of a bent magnet into an arc, making an angle theta at the center or at the point O, like it is shown in the figure. So now let us try to understand few special cases connected with this one. So this is what our earlier conclusion was. So m dash is equal to 2m sine theta by 2 by theta. This is what our conclusion was, right? So this is the magnetic dipole moment of the magnet, which is bent such that the angle subtended by that bent magnet is theta. Okay. So if theta is equal to pi by 2, like this, the magnet is bent such that angle made by this bent magnet is how much? Pi by 2, 90 degree. If this is the situation, what will be the resultant magnetic dipole moment? Let us try to find out that. M dash is what? 2m sine theta by 2 by theta. So I am going to replace this theta with pi by 2. Let us see what happens. This is what m dash is. So now I have replaced theta with pi by 2. If this theta is replaced with pi by 2, you will have pi by 2 into 2, 4, pi by 4. And this theta is also replaced with pi by 4. Sine pi by 4. Pi by 4 is what? 45 degrees. Sine 45 is? It's 1 by root 2. Isn't it? So 1 by root 2, if it is further simplified, you will have something like this. 2 root 2 m by pi. Okay, here you will have 1 by root 2. 2 2 is 4, 4 by root 2. If you go with the rationalization, what you will have? 2 root 2 m by pi. That's what our conclusion is going to be. Okay. Now, if theta is pi, what happens then? If theta is pi, this is the case. Theta is pi in the sense the magnet is bent in the form of a semicircle. Okay. So here magnetic length, very simply you can find out it's equal to diameter, isn't it? Okay. Anyways, with the help of theta, we'll try to find out what is the resultant magnetic dipole moment when the bar magnet is bent in the shape of a semicircle. So m dash is equal to 2m sine theta by 2 by theta. This is what our equation is, master equation connected with the bent magnets. Here theta value is replaced with the pi. So this theta is also replaced with pi. Sine pi by 2 is 1. So the answer is 2m by pi. So the resultant magnetic dipole moment, if it is bent in the form of a semicircle, is 2m by pi. If theta is equal to 2 pi, what does it mean? It is bent such that, completely it is converted into a circle, something like this. Pi plus pi, 2 pi. If this is the case, where you will be imagining South Pole and North Pole? If there are two ends, one pole, one end you can call it as South Pole, the other end you can call it as North Pole. But here, are there any ends? No, there are no any ends. So what kind of thing is this? Let us try to understand this. This is what the resultant magnetic dipole moment is, right? So here theta value is 2 pi. So if I replace this theta with 2 pi, 2 gets cancelled and I am left with sin pi. Sin pi equal to 0. If sin pi is 0, this m dash will be 0. So the resultant magnetic dipole moment will be 0 if a bar magnet is bent, if a thin bar magnet is bent in the shape of a circle. Okay. So this can be a conceptual question. Now let us talk about this one. When a magnet in the form of an arc of circle making an angle theta at the center having magnetic moment m is straightened, then, so earlier what was the case? A magnet is taken here. Let me show you once. This magnet is bent such that it is making an angle theta. Now the situation is, let us say you have started like this only, like you are looking at a bent magnet making an angle theta, its magnetic dipole moment is m. Now it is straightened. Now it is straightened. Then what happens? Let us see. Anyways, we'll extrapolate the discussion. So this is the situation. Now it is straightened like this. Earlier it is making angle theta, and at that time what is its magnetic dipole moment? Capital M is magnetic dipole moment. Now it is straightened like this. So the resultant magnetic dipole moment is expressed like this. The way in which we have proceeded earlier, in the same way we have to proceed, and we'll get something like this. Okay, m dash is equal to m theta by 2 sine theta by 2 gives us magnetic dipole moment of this straightened magnet. Okay, right. Now let us have a look at this one. It's a kind of small problem. A long thin magnet of moment m is bent into a semicircle. The decrease in magnetic moment is, so a long thin magnet of moment m is bent into a semicircle. If it is bent into a semicircle, what happens to the magnetic length? Magnetic length decreases. If magnetic length decreases, what happens? The magnetic dipole moment also decreases. So here he is asking about decrease in the magnetic moment. He is not asking about final magnetic moment. He is asking about decrease in the magnetic dipole moment. So all that you need to do is you have to find out final magnetic moment and just take the difference between this m and final magnetic dipole moment. You will get a decrease in the magnetic moment. So this is what equation you can use. Okay, if it is bent such that it makes an angle theta, magnetic dipole moment can be expressed as 2m sine theta by 2 by theta. Okay, so it was said that it is bent into a semicircle. Semicircle in the sense theta value will be pi. So replace with pi, what you will get? 2m sine pi by 2 by pi. Sine pi by 2 is nothing but 1. So m dash is equal to 2m by pi. So this is the final magnetic dipole moment. Earlier it was m, now it is 2m by pi. So it is decreased. So how much is the decrease? M minus m dash is equal to, this is initial magnetic dipole moment, this is final magnetic dipole moment after it is bent into a semicircle. Okay, so m minus m dash is how much? 2m by pi. So if you take out m common, you will have 1 minus 2 by pi. Okay, so that's how you can solve this problem. Let us have a look at this one. A magnet of magnetic moment m is in the form of a quadrant of a circle. Quadrant of a circle in the sense like 1/4. If it is straightened, its new magnetic moment will be. So earlier it was like this. Now it is straightened like this. So earlier the distance of separation between these two poles is less when compared to this distance of separation between poles, isn't it? So what happens to the magnetic dipole moment? It increases. Magnetic dipole moment of this magnet will be more than this magnet, isn't it? So we have already seen one equation. If a magnet is bent such that it is making an angle theta at the center of curvature, then the magnetic dipole moment, if it is equal to m, and later if it is straightened like this, the resultant magnetic dipole moment will be this one, m dash is equal to m theta by 2 sine theta by 2. Just replace this theta with pi by 2, I will get the answer. Theta is replaced with pi by 2, 2 sine, this theta is also replaced with pi by 2, pi by 2 into 2, 4, pi by 4. Sine pi by 4 is what? 1 by root 2. And if it is further simplified, you will have something like this, 4 by root 2 will come in the denominator. So if it is further simplified, you will have root 2 m pi by 4. Rationalize with root 2, you will have m pi by 2 root 2. Okay, so that's how you can solve the problems. Thank you, students. With this, I will close the session. And in the further sessions also, we will be dealing with a few problems connected with magnets, if they are bent, if they are cut, and if they are aligned at different angles, what is the resultant magnetic dipole moment? That also we are going to find out. Okay, thank you, students.